Hola. Hey, you probably feel like you're so sick and tired of moving on so quickly. The reason why I'm trying to do so is because no matter what happens with the rest of the year, I don't know when school's going to be back in session, or if so, there's so many unknowns. But regardless, we need to finish this course because it's a university course, right? It's a college class. So we need to finish, and we're more than halfway, but I just am worried that we're going to run out of time. So that's why I'll probably have you guys be moving as quickly as I can. I'll not overloading you too much, and I'm not going to have you do any of the reading quizzes right now because we just don't have time to worry about that stuff. So which I don't know if that is a good thing or bad thing, but anyway, so far we have talked about expected value and standard error, but we've only learned EV sum and SE sum. So we're only doing the sum of the draws. So today I'm going to teach you EV percent and EV average. So EV and SE percent, EV and SE average. So we're first going to start with the percent. So basically, when we're looking at a box model and we have, ones and zeros in the box, well, the expected value for the percentage of ones of the draws is just equal to the population percentage, right? So if I have a box model, this is in a really dark color, let me switch colors. So if I have a box model with like 1, 1, and 2 zeros, right? Then this percent, EV percent, would be just the percent of ones in the box, right? So I would expect 33% of my draws to be ones because that's a third. So that's exactly what EV percent is, right? It just matches what the population is. The standard error, though, for the percent of ones is the SD of the box divided by the square root of the number of the draws times 100. And then that will be a percent. Okay, so those are the formulas, right? EV percent is just the percent of ones. Okay. And then the SE percent is SD of the box divided by square root of draws times 100. You will always have these formulas, so you don't need to memorize them. You just need to know how to use them. So let's do an example. So this example, we have 100,000 people, and we know that 20,000 are minorities. So if you take a simple random sample of 400 people, how many minorities do I expect to get in my sample? And then find the standard error. So this is the number, right? Not the percentage, just how many out of my 400. So let's draw a box model just to show what this looks like. And you may not need to do this. Like if you already know the answer to this, that's great. But I just want to connect it back to previous information. So we have 20,000 are minorities in the 100,000. So that is 20,000 out of 100,000 is 20%, right? So if 20% are minorities, then I could set up a box model multiple ways, okay? Probably infinite number of ways, but anyway. So if I want to stick to percentages, because that might be easiest, then I could go because say I just do 10 tickets, or if you want to do 100 tickets. So if you want to do 100, say I could go 20 out of my 100 are ones, because those represent the minorities in the population. And then the other 80% are not. So those would be my zeros. So that's one way that I could set up the box model. If I divided both of those by 20 and just got the smallest numbers, then I could use just 1, 1, right? 1, oh, that's supposed to be a square. Yeah, and then 4 zeros, because remember they got a total to 5, right? 1 out of 5 is 20%. Or I just divided these by 20. So notice both of these models are correct for the problem, and there would be more that would also be correct. It's just whatever makes most sense to you. Whether you just like it to be out of 100 for 100%, or just like to deal with the smallest numbers possible, okay? So then how many minorities? Well, the easiest thing that I can think of without even using EV sum for the formula is, okay, if 20% are minorities in the population, then what's 20% of 400? So 20% times 400, which is what the EV sum is going to be, okay? I just think first it makes sense to just talk about it's 20% of your sample. So I think that's going to be 80 people. And then the standard error, so that will be the SE sum. Okay, well, first we need to find the SD. So this is using the SD shortcut again, which is good that we're reviewing this. So it's the large number on the tickets, which is just a 1, minus the small number on the tickets, which is 0. So whenever you have the tickets just 1 and 0, you almost don't need to do this first part of the shortcut because it's just 1 minus 0. But anyway, and then times the fraction of 1s and 0s. But I'm going to do the decimal just because, so it'd be 0.2 times 0.8, or 1 out of 5 times 4 out of 5, or 20 out of 100 times 80 out of 100. Notice all those ratios are the same. So whatever that number is, I should have that ready for you, if I was on top of it. So then that's going to be whatever the SD is times the square root of the draws, which is square root of 400. Okay, so I'm going to pause this for a second to plug those in. Okay, so I got 0.4 is the SD. So then that would be 0.4 here. Then this would be 8. So it would be 0.4 times 20, which would be 8. Okay, so how many can we expect in our sample of 400 to be minorities? Well, we can expect 80 of them, which makes sense because 80 out of 400 is 20%, give or take 8 people. So this is our wiggle room, like give or take how much. That's always going to be the standard error or the standard deviation if we're referring to just one thing. But okay, and then part B is what percentage of minorities do I expect to get in my sample, and then find the standard error for the percent. Okay, so now instead of number of minorities in the sample, we're looking at percentage. So if you go back, EV percent is just the population percentage. So what's the percent of minorities in the population? Well, it's 20%. So that's the EV percent. You should never get EV average. Well, EV average we're going to talk about in a minute, but you should never get EV percent wrong ever, because it will literally state it for you. So EV percent is 20%. And then the SE percent now that we already know the SD, right? So I'm going to use this formula up here, which is the SD of the box. So the SD of the box is 0.4 divided by the square root of the draws times 100 to make it a percent. Because that 0.4 divided by square root of 400 will just be the decimal. So then when we multiply that by 100, it'll be 2. So that is the EV percent, is we can expect 20% of our sample to be minorities, give or take 2% of our sample, which 2% is 8 people. So anyway, so that's how you find EV percent and SE percent. So now, just some important information that when we have a large number of draws, I'm going to use this highlighter. The percent of ones in the draws will follow the normal curve. And the average of this curve will be the EV percent, and the standard deviation will match the SE percent. So as long as we have this large number, and maybe you're wondering, well, what the heck defines a large number? Usually for the central limit theorem to apply, which is what this is. Okay, I'll talk more about that in the future, but we like it to be a minimum of 30. Like 30-ish is our large number that we say, okay? And then the other thing, the probability histogram for the sample percentage will follow the normal curve when the sample is, so it has to be large, like we said, and then it has to be a random sample. So like we talked about in chapter 19, you can't just sample the first 30 people because that's truly not a random sample. So that may not follow the normal curve because it's not a random sample, okay? All right, so let's now use this information with the normal curve and what we learned with EV percent to answer this question. I need to move. Hold on, I'm gonna try to move this out of the way. There we go. Get out of there. Okay. So we have in a certain town, 25% of college kids own a car, okay? And then, so if we take a simple random sample of 400 of these college students, what is the chance that less than 20% of them own a car? All right, so we're using the EV and SE percent to find the chance of it happening. So in order to find that, we need to first just define what is the EV percent and what is the SE percent, okay? So EV percent, like I said, never miss this, is just the percent of the population or percent of ones in the box model. And that's exactly what they define right here. Hey, this percentage of people own a car. Well, that's what we expect from our sample, right? Makes sense. If the population has a fourth of them own a car, our sample should have about a fourth of them own a car. So now the SE percent, well, now we need to find the SD of the box model. So if I made a box model for this, one way I could do it is I could just have 1 for those that own a car, and the remaining percent